Good day to everyone. So in the last video we have discussed about the basics of the fluids, the viscosity and the Archimedes principle, and how this viscosities actually affect the flow of the liquid or flow of the fluid. So based on the viscosity of the fluid, the flow of the fluid can be separated by the two different flows, which is one is called as a laminar flow and another one is the turbulent flow. So this laminar flow is occurred when the critical velocity of the liquid is means the velocity of the liquid is lesser than the critical velocity, and the turbulent flow will occur when the velocity of the liquid is actually greater than the critical velocity. Okay, so this happen. So from this we can define the critical velocity. So the critical velocity is of the liquid is a velocity below which the motion of the liquid is laminar flow or laminar or ordered flow, and if the critical force is greater than the velocity of the liquid is greater than the critical value, then the motion of the liquid becomes turbulent. So suppose if you consider the fluid actually moving from one point to another point, and suppose the velocity is actually changing continuously during the flow, at some point the critical velocity reached, so that after the critical velocity the flow will be turbulent, so that before this critical velocity the layers is actually not mingled with each other. However, when the velocity is crosses the critical velocity, then the turbulent flow of the liquid will occur with the mixture of the layers, and each and every layer which is moving with the different velocities, and you can see the whirlpool like structures in the flow of the water or flow of the fluid. So if you consider this critical velocity of the liquid is actually may depending upon the three different properties of the liquid. So suppose if you consider that Vc is the critical velocity, which is actually depending upon the viscosity of the coefficient of the viscosity of the corresponding liquid, as well as the density and the radius of the capillary tube in which the liquid is flowing. So that if I take the R is the radius of the capillary tube, so this will be the critical velocities may be based on this coefficient of viscosity, density of the liquid, and the radius of the capillary tube. So the relation which I can write as Vc, which is proportional to the eta divided by rho times of R. Okay, so the velocity is directly proportional to the viscosity of the liquid and inversely proportional to the density as well as the radius. Suppose if I add the proportionality constant, so that I can equate this equation, which is equal to k times of eta divided by rho into R. Here this k is the Reynolds number. So this equation can be rearranged to find out the Reynolds number k, which is equal to Vc times of rho into R divided by eta. So the significance of this Reynolds number is that the value of this Reynolds number is actually determines the nature of the liquid flow through the capillary tube. So in case of the apparatus, and if you consider the apparatus is geometrically similar, and whatever the actual dimension is, so the turbulence occurred in the same constant value of the Reynolds number in all case of the liquid flow. So the flow will be steady and streamlined, suppose in like a laminar flow in each individual case, until this number is not exceeded. So usually the value of k is in between, suppose in the range of 2000 to 3000. Suppose if suppose the Reynolds number's value is lesser than the 2000, then the flow of the fluid will be laminar. And if it exceeds the value of 3000, then the nature of the flow is actually turbulent. So this the Reynolds number is actually defining the nature of the flow of the liquid. Suppose if the Reynolds number of the liquid is in between the 2000 to 3000, then the the liquid is actually in the transition state, either neither laminar nor turbulent, but it is in the transition state between these two different flows. Okay, suppose if you consider a capillary tube and the fluid actually flowing from one part to another point of the capillary tube. So how this flow is actually occurring in this tube? Suppose if you can or what causes the flow? So this the answer of this question is the pressure difference. Suppose if you consider the pressure in the one point is taken as a P1, another point is P2, and suppose if the P2 is actually the P1 is greater than P2, then the pressure is then the liquid is actually moving from the higher pressure point to the lower pressure point. That means it is actually flow in this direction. Suppose if the P2 is greater than P1, then the fluid flow will be in the opposite direction. So the fluid will always flow from the high pressure region to the low pressure region. So that I can write the flow rate of the liquid can be taken as P1 minus P2. Suppose if P1 is greater than P2, then I can write the flow rate equation as P1 minus P2 divided by R. So here R is the resistive force occurred in this liquid during this motion. Thus this resistive force is usually comes into this picture due to the viscosity of the corresponding liquid. So the flow rate is actually directly inversely proportional to the resistive force, that means the viscosity of the corresponding liquid. So the viscosity is increased, then the flow rate will be decreased. Otherwise, it is inversely related to each other. Suppose if you consider the viscosity of the liquid is nearly zero, then the fluid is actually frictionless. So that is R equal to 0. Therefore, the flow rate will be almost infinity. That means there is no resistance occurred in this fluid flow. So based on the friction, the frictionless or viscous flow, you can see the flow. The shape of the flow will be different based on the viscous or non-viscous fluid. Suppose if the fluid is actually non-viscous medium, then the flow will be uniform throughout the capillary tube. Whereas if you consider the viscous fluid, then the velocity is actually maximum at the middle of this middle of the tube, and is actually decreasing in the once if you are moving towards the wall of the tube. So that is why it is having the parabolic like path, which is we already seen in the last class. So in this figure you can see that the flow of the non-viscous and the viscous fluid. So you can see this in the viscous fluid, the flow is actually greater at the midstream because of this drag of the boundaries, and we can see the non-viscous fluid so that the velocity is equal in all the direction. So we can see this figure where the Bunsen burner. So this is actually the viscous fluid actually, which is having the velocity at the midpoint of this the fluid, the flame of the burner. So you can see that the velocity is high in the midpoint, and if you moving away from this midpoint, you can see the parabolic like structure. Whereas if you consider the other non-viscous fluid which is flowing through this tube, so you can see that the non-viscous flow, that means the flow is actually uniform in all the directions. Okay. So this is the best example for the viscous and the non-viscous flow of the fluids. Suppose if you consider the viscous fluid which is actually moving in this moving into the capillary tube, so that the velocity is actually maximum in the midpoint of this capillary tube, and it is once if you are moving away from this midpoint, or if you are facing towards the tube sides of the capillary tube, then the velocity is actually decreasing. So that you can easily find out this velocity of the capillary tube. Then the relation is actually given by. So that means the average velocity of the fluid flow, liquid flow in this in the capillary tube can be given as V, which is equal to P1 minus P2. That means the pressure difference between the two points of the tube divided by 4 times of eta times of L into A squared minus R squared. So here the A squared is the radius of this capillary tube, and R squared is the the very small area which we have considered. If we consider the small area, and this is the radius of the small area, so that you can see that the velocity is actually equal to this point. Suppose if the radius is actually equal to 0, this is r equal to 0, then this relation is actually equal to this point, which is actually giving the parabolic relation. That means v is equal to, that means the v is actually proportional, which is equal to some constant into a squared. That means this everything is a constant. So some constant into a squared, which is actually the parabolic the relation. So that if you vary the velocity, if you vary the radius, you can get the parabolic like velocity change in velocity in the viscous fluid. So we can derive this equation once if you consider once we can in this class. And how much fluid is actually the volume of the fluid actually flowing from in this capillary tube per second can be given by the derivation v is equal to pi times of p1 minus p2 divided into the power a power 4 8 pi times of pi into L, rho into eta into L, so that the volume of the liquid which is flowing through the unit in the second, which is actually directly proportional to the radius as well as the pressure difference, but it is inversely proportional to the viscosity as well as the length of the capillary tube. Okay, so we can derive these two relations, the two equations, velocity as well as the volume, in the small derivation. So with this formula is actually known as the Poiseuille's formula. So the Poiseuille's formula is given by the Poiseuille's formula for the velocity is given by this, and Poiseuille's formula for the volume is given by this relation. So we can derive these two equations with which we just consider a capillary tube which is having the length of L, and the radius is taken as A, and pressure at the one end is taken as P1 and another end is taken as P2, and generally we can take the pressure P1 is greater than P2, then how this flow is, the flow of the liquid is actually happening in this capillary tube, and what is the corresponding velocity as well as the volume, which we can find it out. So here we are going to derive the Poiseuille's formula for a flow of a liquid through a capillary tube. So this is the capillary tube which we are considering. This capillary tube is having the length of L, and the radius is actually taken as A, and the pressure is actually at the one point, at this point is taken as P1, and on another point the pressure is taken as P2. Usually, so we have considered the P1 is greater than P2, so that the flow of water is actually from this direction. So if you consider a steady flow of a liquid with a coefficient of viscosity is taken as eta is the coefficient of viscosity of the fluid, which is actually flowing through this capillary tube. This the velocity of the liquid is taken as v, small v, which is actually maximum at the axis, along with the axis, and it is actually 0 around, it is actually going towards the wall of the tube. So we are assumed that there is a no radial flow of the water. That means the flow is actually in this direction. There is no flow of the water in the opposite direction. So we are just assuming that the flow is actually going only in the one-dimensional direction. So to find out the velocity of the fluid which is passing through this capillary tube, we are going to consider a small section of area of section, cylindrical cross section of this tube, which is having the radius of r, and the thickness of this the cross section, the small cross section is taken as dr. So that this cylinder is actually having the inner radius of r and the outer radius of r plus dr. So the inner radius is actually taken as r, and the outer radius is taken as r plus the other section, small cross section dr. So this is the radius of the corresponding cylindrical section we have taken, which is having the length of L. And so the velocity of this liquid at this inner shell taken as the velocity at this inner radius shell is taken as v, and so in the velocity at the outer radius is taken as v minus dv, because once if you are moving away from this center point, the velocity is actually decreasing, so that I can take the small deviation in the velocity is taken as dv minus taken as dv, so that the volume the total velocity is actually taken v minus dv. Okay, and therefore the rate of change of velocity is taken as this small area is taken as a dv by dr, which is the rate of change of velocity over the dr. So what we are going to find is what we are going to do is we have to find out the velocity of the liquid as a function of the radius r. Then if you find out the expression, then you can integrate the expression so that you can find out the radius in the whole capillary tube. Okay, so we know that we can find the pressure of this the pressure which is actually P1 and P2. So I can write the pressure from P is equal to F divided by the force divided by the unit area, or I can write the force which is equal to P times of the area, and we already know this area of cross section, so that I can just write this the pressure is actually taken as the difference between the point P1 and P2, that is taken as the pressure, so that I can write this as P1 minus P2, that is the pressure difference between the two points of the capillary tube, and A is the area, which is I can take it as a pi r squared. That means if we consider only this small cylindrical cross section, then I can write this as a pi r squared. That is the force which is actually causing this fluid flow. Okay, so that means this force is nothing but the driving force which causing the flow of the fluid, which is equal to this f of d, or f I taken f1, which is equal to P1 minus P2 of pi or multiplied by the pi r squared. So this is the driving force. So once the fluid is actually flowing from in this direction, there is a backward resistive force which is actually opposing the fluid flow. That is actually depending upon the viscosity of the fluid, so that I can write the backward dragging force, which can be written as F2, which is actually equal to which is actually dependent upon the coefficient of viscosity eta into the area and the rate of change of velocity dv by dr. So this is the backward dragging force with the minus sign, because this minus sign means once if you are moving away from this radius, means from the center, the rate of change of velocity is actually decreasing, so that I can add the negative sign in this formula. Okay, so you can already find this area of cross section of this small cross section. That means A can be written as the circumference into the length. So the circumference is taken as a 2 pi times of r minus into multiplied by the length is taken as a L, so that the area is 2 pi r into length. That means this is the area of cross section of the corresponding the capillary tube, so that I can write this backward dragging force F2, which is equal to minus eta 2 pi r into L dv by dr. So this is the backward dragging force. So at a steady state, this dragging force is equal to this driving force, so that at steady state this F2, which is equal to the F1, so that I can just substitute in the values of equation 1 and 2 here. So the F2 is nothing but the minus eta 2 pi RL dv by dr, which is equal to this F1 force F1, which is nothing but the P1 minus P2 pi r squared. Okay, so from this equation I can just neglecting this pi as well as this r and this r, so that I can find out means I can simplify this equation in terms of finding out the rate of change of velocity, so that I can write this in terms of minus dv by dr, which is equal to P1 minus P2 into r divided by this eta, 2 times of eta into L. So that is the rate of change of velocity as a function of this dr. so that this is taken as equation 3. Suppose if I integrate this equation, I can get the velocity, so that if I integrate on the both sides, so minus of dv by dr, which is equal to, so the constants you can take in the outside, so, or I can write this as integration of dv minus of dv, which is equal to integration of p1 minus p2 divided by 2 eta L and integration of r into dr. I can just rearrange this equation in this form with the integration, and if you integrate this, we can get the minus v, which is equal to p1 minus p2 divided by 2 eta L into r squared divided by 2 plus the integration constant. So, C is the nothing but the integration constant, and if you want to find out this integration constant, so in this equation if you put r is equal to a, that means if you consider the radius of the radius taken is r is equal to if you take r is equal to a, so at this point the velocity is equal to 0, so that if r is approaching the a, then the velocity which is equal to 0 at the wall of the near the wall of the pipe, with the capillary tube, so that I can write this equation for r equal to a, v equal to 0. So I can write this 0, which is equal to p1 minus p2 divided by 2 eta L times of, I can just multiply this 2 and 2, I can get 4 times of eta L into a squared plus c. So from this equation I can calculate the value of c. The c is actually having the value of negative value of p1 minus p2 divided by 4 eta L times of a squared. So this is the value of the c, so that I can just substitute this value of c into this equation, into this we've taken as the fourth equation. I can substitute the c value here, so that I can write this equation 4 as minus v, which is equal to p1 minus p2 divided by 4 eta L times of r squared minus, because this c is having the sign of minus, so I can write p1 minus p2 divided by 4 eta L times of a squared. Okay, so this is the velocity. So I can just simplify this equation, just rewriting the equation minus v, which is equal to, can take the constants outside, p1 minus p2, we get a common layout taken outside, 4 eta L times of r squared minus a squared. So here you can see have the negative sign. So if you want to neglect this negative sign, you can just multiply the negative sign on both sides and rearranging this value equation here, so that I can write v is equal to p1 minus p2 divided by 4 eta L into a squared minus r squared. Okay, so this is the formula which we have discussed earlier. So v is equal, in the previous experiment, vs is equal to p1 minus p2 divided by 4 eta L into a squared minus r squared. So once if the r is actually approaching 0, that means at midpoint you have the maximum velocity of this quantity. If r is non-zero value, then you can multiply this r squared value from this v, so that this the velocity is actually decreasing once if you are moving away from this r. So that if you put r equal to 0, the velocity relation is actually the velocity relation, but then the radius is taken as the parabolic equation. So this is the average velocity of the liquid flowing through the capillary tube. So suppose if we take this as equation 5, and in this equation 5, using this equation, you can easily calculate the volume of the liquid that is flowing per second through the capillary tube, or through the shell. We can easily find out. So the volume of the liquid flow out per unit second or per second, which is taken as the dV, which is equal to the area of cross section of the shell with radius r and thickness dr multiplied by the velocity of the flow. So we can easily write the area of cross section of the shell with the radius r and the thickness dr as taken as a 2 pi r into dr multiplied by the velocity of the flow, which is we already calculated here. So I can just substituting this equation 5 into this here, so that I can write this P1 minus P2 divided by 4 eta L times of a squared minus r squared. So that is my dV, value of dV. Here you can just cancelled out this 2 and this 2 times, and I can write the final equation dV, which is equal to pi of P1 minus P2 divided by 2 times of eta L a squared r minus r cube into dr. So this is the change in volume, so that I can find out the total volume V. That means that just integrating this equation. Suppose if I take this equation as equation 6, I can integrate this equation from the between the limits of r equal to 0 to r equal to a, so that I can find out the V, which is equal to the limit integration of 0 to a by P1 minus P2 divided by 2 eta L into a squared r minus r cube dr. So I can take the constants outside, so that pi P1 minus P2 divided by 2 eta L, and suppose if I integrate this value, I can get a squared r squared divided by 2 minus r power 4 divided by 4, the limits of 0 to a, and if you substitute the values of the limits, I can get pi P1 minus P2 divided by 2 eta L, and here you can the a power 4 divided by 2 minus a power 4 divided by 4. So I can take the common LCM, you will get the 4 here, and you get the 2 power 2 into a power 4. This 2 into a power 4 minus a power 4, you will get the a power 4, and the 4 is taken commonly outside. I can write this the final equation as pi P1 minus P2 divided by 8 rho L into a power 4. So that is the total volume of the flow, volume of the water, the volume of the liquid which is flowing per second into the capillary tube, which is we have already said in the previous case. So 5 into P1 minus P2 divided by 8 eta L by a power 4. Here you can see that this volume of the flow is actually directly proportional to the radius of the capillary tube, so that if the area is increasing, the fourth power if the volume is actually increasing with this multiplication. Suppose the viscosity of the liquid is actually high, then the velocity will be low. Similarly, if the length of the pipe is very large, then the volume of the flow is also decreases once if you increase the length of the pipe. Okay, so we have derived the Poiseuille's formula for the velocity as well as the total volume of the flow which is passing through this capillary tube. Suppose if you are doing an experiment, that means the Poiseuille's method to determine the coefficient of the viscosity of the liquid. So you can just do an experiment, and then you can find out this volume and velocity, so that you can just substituting this equation, so that you can find out the viscosity of the corresponding liquid.